Before we start graphing rational functions, let's look at some of their behaviors. So first, a rational function is any function that results when we divide two polynomials. Some examples: f of x equal to 2x plus 3 over x to the fifth plus 8x minus 1, g of x equal to 2 over x plus 4, and h of x equal to x squared over x minus 1. Anytime we're working with rational functions, we need to make sure that we're not dividing by 0. And there's a couple of things that can happen whenever we do have that division by 0. To explore a little bit of what happens, let's consider the function f of x equal to x plus 1 over x squared minus 1. Anytime we're working with rational functions, a good first step is to factor both the numerator and the denominator. That gets us x plus 1 over x plus 1 times x minus 1. There are two types of terms that could appear in the denominator, both of which are appearing here. The first is if it's common with the numerator. In this case, the x plus 1 is both on the top and the bottom. Any common factors between the numerator and the denominator that are canceled result in what's called a removable discontinuity. In this case, that would mean x plus 1 equal to 0, or x equal to negative 1 is a removable discontinuity. This means that there's actually a hole in the graph at that particular point. And when we draw the graph, we use an open dot to denote something like this. The other type of factor that could appear is something that appears in only the denominator. This is going to result in what's called a vertical asymptote. For this one, we would have x minus 1 equal to 0 or x equal to 1 be the vertical asymptote. This is a vertical line, which is usually denoted by a dotted line in the graph, and it's a line that the function approaches, but never actually touches. So it gets infinitely close to this line, but it never actually touches. Here's a picture of this function. We see the open dot at negative 1 and the vertical line at x equal to 1, indicating that vertical asymptote. And we can also see how the graph gets really close to this line. Another important thing to consider is the end behavior, and there are three possible things that could happen. The first two are a type of horizontal asymptote, and the third is a type of slant asymptote. Both of these are just lines that the ends of the graph approach but do not touch. But there are three different cases of what could happen. The first case happens if the degree of the denominator is larger than the degree of the numerator. In that case, the horizontal asymptote would be y equal to 0 every time. As an example, f of x equal to x over x squared plus 3x minus 4. The degree of the top is 1, the degree of the bottom is 2. Since the bottom is larger, my horizontal asymptote will be y equal to 0. Here's the actual graph, and you can see as x gets really, really big or really, really small, this graph approaches that y equal to 0 line. The second case is if the degree of the numerator and the degree of the denominator match, if their degrees are the same. In this case, my horizontal asymptote would be y equal to the ratio of the leading coefficients. As an example, x squared over 2x squared plus 4x plus 3. In this case, each of the leading terms will be the x squareds. I have a coefficient of 1 on the top and a coefficient of 2 on the bottom. This would give a horizontal asymptote of y equal to 1/2, and I can see that in the graph here. I have the dotted horizontal asymptote of y equal to 1/2, and I can see that as x gets really big or really small, I'm approaching this line. For the final case, let's consider when the degree of the numerator is exactly 1 larger. Something like f of x equal to x squared minus 3x plus 2 over 2x minus 1. In this case, we actually want to divide the polynomials. We need to know x squared over 2x. That would be 1/2 x, so we write that at the top. Then we multiply, subtract, and bring the next number down. Multiplying would give us x squared minus 1/2 x. Move our negative sign all the way through, That would give us negative 5/2 x, and then we bring down the 2. Negative 5 over 2x divided by 2x is negative 5 over 4. And then we multiply and subtract. 2x times negative 5 over 4 is 5 over 2x, negative 5 over 2x. And negative 5 over 4 times negative 1 is positive 5 over 4. We subtract to get 3/4, and the actual quotient is the slant asymptote. That means y equal to 1/2 x minus 5 over 4 is our slant asymptote. The ends of the graph will actually approach this slanted line. We can see the graph of that function here. And this slanted line is that slant asymptote that we just found.